There have been a ton of do-it-yourself foundries over the years, but almost all of them suffer from the same drawback. You have to continually purchase new fuel in order to keep them running. So in this video, I'll be giving the paint can forge a modern makeover by converting it into the ultimate 2000-degree desktop electric foundry. Let's start this project off with the main body of the kiln. For this, I'll be using a standard 1-gallon paint can, which can be bought in most stores. It needs to be metal though, because the exterior will get pretty hot during operation. To kick off the build, we first need to poke a few holes in the bottom of our can. I recommend using a drill for this, but as you can see, a pocket knife will also do the trick. These holes are for a set of 2.5-inch machine screws with nuts, which will be used to secure the kiln body to a wooden base later on. At the same time, we'll also need to cut a somewhat larger opening in the bottom for the heating element wires, along with another screw hole to mount a ceramic terminal block. I recommend cutting a pretty wide opening around the electrical connections, just so there's less risk of the metal body touching live wires. You may notice that I didn't fully remove the metal from the opening yet, and that I instead covered over it with electrical tape. This is just a preventative measure to keep the insulation inside the body while I'm working on it. And speaking of insulation, let's talk about that now. While designing this kiln, I tested several types of insulation, ranging from a DIY mix of perlite and cement, which crumbled at high temperatures, to a professional, castable refractory, which was stable but didn't keep the heat in very well. Take it from me, the solution I'm about to show you is probably the best one all around. It has stood the test of time in many homemade foundries, and it's quite a bit cheaper and more durable than firebrick, so it comes highly recommended. Before we deal with the insulation itself though, we'll need to create an insert to shape the kiln's interior. For this, I recommend a combination of hot glue and carvable foam, which can both be bought at Walmart. Carve and glue the foam into a 6-inch tall, 3¼ inch wide octagon with 4 connected arches. These arches are just over 1/4 inch deep, and they'll form a nice channel in the refractory for the heating element to rest in. Once the foam carving is done, we can move on to our kiln's outer layer of insulation, which will be made from a section of 1-inch thick ceramic blanket. For a 1-gallon paint can, we'll need to cut out a 6.5-inch circle for the bottom and a 20-inch by 6-inch sheet for the sides. With the KO wool packed in, there should be just enough room to fit the foam insert with about 1/2 inch to spare. I had to peel off a roughly 1/4 inch layer from the ceramic wool to get this much clearance. Now, with the ceramic wool cut to shape, all we have left to do is carve one last hole in the side for our thermocouple and take the body outside to add the castable refractory. For this build, I'll be using Castilite 30, which is known for its durability, high operating temperatures, and crack resistance. I bought a 5-pound bag of it along with my ceramic blanket from hightemptools.com. You can find links to all the materials I used in the video description. To insulate our kiln, we first load in our ceramic blanket and gently wet it with a damp cloth or paper towel. This should stop the ceramic from absorbing the water in our refractory while it cures. Then, we dump our 5-pound bag of Castilite 30 into a suitable container and add 1½ cups of water. This gets mixed together thoroughly until we are left with a mixture similar to wet sand. Once the desired consistency is achieved, lay down a 1/4 to 1/2-inch layer on the bottom of the kiln, load in the foam insert, and pack in as much refractory as possible, making sure to fill in all the voids. Try to get this done within 30 minutes of mixing the Castilite. As soon as everything is filled, place a damp cloth over the exposed refractory and set everything aside to cure for 1 to 2 days. And while things are hardening up, we can start putting together the base of our kiln. I'll be using particle board and angle iron, but feel free to use whatever materials you have on hand. For the control circuitry going into the base, we'll be using this kit made by Inkbird, which includes both the PID controller and the solid-state relay needed to control the heating element. It also comes with its own K-type thermocouple, but you can just toss this out, because we'll be using this fancy high-temperature one instead. To connect everything up to the controller, just follow the schematic included on the side of the module, which I've simplified here. As long as you own a screwdriver and some spare wire, you should be all set. But if you need some wire and a way to plug your circuit in, just go by your local supermarket and pick up a 12-foot extension cable for a few dollars. You can hack this apart with wire cutters or a pair of scissors into all the wire you need. Returning to our kiln body, everything seems to have solidified properly after just 48 hours, so we are clear to take out the foam insert. I scrape out most of mine with a putty knife and use a propane torch to burn out the remaining bits. Then, I remove the last bit of metal from the bottom of the can and drill 2 holes into the base for the heating element. And with that, the majority of the body is done. So now, let's take care of the heating element. For this, we'll be using a pre-made 3000 watt coil, which can be bought on Amazon for pretty cheap. If you live in a 220 volt region, this should work just fine as is. But for 120 volt users like me, the element will need to be cut down a little. After stretching out the element to separate the windings, find where the resistance measures 9 ohms and cut there. Then, stretch the 9 ohm section to roughly 40 inches in length and begin pressing it into the kiln body. As soon as everything is fitted, screw the ends of the element into one side of the terminal block, connect the power wires to the other, and complete the final assembly. All in all, I think it turned out quite stunning for a paint can foundry. At this point, before we jump into using this kiln, we'll need to perform a quick bakeout. Set the temperature to something like 600 degrees Celsius and let it run for about an hour. A lot of steam should come off initially, and once it looks like no more is being generated, the setup is finally ready for its maiden voyage. By dropping in a crucible and cranking up the temperature to 800 degrees Celsius, this kiln can easily melt large amounts of aluminum in no time flat, making it super handy for DIY metal casting projects. Of course, almost any foundry can melt aluminum these days, so what about a more challenging metal like copper? Well, after setting the temperature to over 1000 degrees, you can see I was able to reduce almost half a pound of this metal to a glowing puddle, and in under 30 minutes as well. Pretty impressive for a paint can. So, there you have it. You now know how to build your own mini electric foundry from readily available materials. Of course, this kiln wasn't just built for melting metals. In some of my future projects, I'll be using this device to perform several high-temperature chemical reactions, including distilling white phosphorus from bones, pyrolyzing plastic into gasoline, and so much more. So make sure you're subscribed for the upcoming fun. And if you'd like to help support projects like this, consider donating or becoming my patron on Patreon. The links, as always, are down below. A special thanks goes out to all the dedicated LabCoatz supporters. Making videos like this isn't always easy, and this one in particular costs quite a bit to develop, so I truly appreciate your support. Stay safe everyone, and I'll catch you next time. LabCoatz out.